Hello everyone. So in this video, what I want to do is just go ahead and recap a bit in chapter 4, and then I'll finish up, I forget the section number, but I'll finish up that section number. It was on, what was it? We'll get to it. All right, so chapter 4 is on exponential and logarithmic functions. The first thing we did in 4.1 was talk about inverse function. So we defined one-to-one. Basically means if you go A to B, A to 1, B to 2, C to 3, then if you go back, you still get a function. So both the directions you get functions. That's the concept anyway. So you can't have A going to another value like that, then it would not be a function, right? That doesn't work. So you can't have that. But you can have another value over here, say D, going to the same value, like 1. But then if you go backwards, like this, then 1 going to D is not a function. So we're defining one-to-one. So you can't have that case in yellow there, so let's get rid of that. All right, so then we defined it, but what I really want you to know is, the horizontal line test. So any horizontal line, so if you have this horizontal line and you move that around, it crosses that parabola more than once. So not one-to-one. So we don't want that to happen for one-to-one. Okay. So we talked about that concept of inverse functions, basically that chart going back. And then we came up with a bunch of descriptions of it. I highlighted that a little later. So if a function is one-to-one, then an inverse exists, and we call it F inverse, like this. All right, so know that basic concept. And the domain and range are interchanged. Again, all these important ideas when you study it. Okay. So, this is the actual definition of an inverse function. So we say F and G are inverses if you can do this composite both directions, and you get X. Okay, then you say G is F inverse, or you can have different notation or function letters. It's fine. So make sure you can do something like this. This will be, when your test isn't coming up for a little while. I'm going to go over all that later, but I just wanted to finish this chapter's lecture notes and then review a bit because it's been a while. So to show functions are inverses, you do that composition. So you compose them together and you get X in both cases. This was a simpler case, and we did some more cases later. Finding inverse functions, the other piece to it. So this process you'll need to be able to do. So you basically do all that, and then go through your examples again, 1, 2, 3, and then you state that's F inverse. And this one is a little more tricky. This is more of a college algebra level case where you're given your G of X, replace your function with your y, interchange, solve. But when you solve, you end up getting a quadratic. So you get x squared minus 2. So that quadratic is actually going to be like this and this. But we know that is not a one-to-one function. Right? So if you had that other side, like this, that's not one-to-one. It fails that horizontal line test. So we don't want any of that. Just get rid of all that stuff. So you have to restrict the domain. So restrict the domain here. Now, you would have known that back here, because back here, x plus 2 must be greater than or equal to 0. It can be 0. The square root of 0 is 0. But it can't be negative, otherwise you'll get an imaginary number. These are all real valued functions, we say. So basically a real axis is your domain, and a real axis is your range. And then the range, basically because your square root function, goes like this, and it's shifted. It's shifted by -1. It's what makes this 0. All right. So this is a good example. No, you'll see that type of question is given on my exams. I may switch it around a little bit where I restrict first, and then you get this one. But once you have the domain and range of your function, you just switch them to get the inverse. Those must be switched. That's what happens. That's the definition. Okay, moving along. The graphs reflected about the line y equals x. Okay, and then each of these individual values, you just switch them to get the function and its inverse. Oops, sorry. Okay. So let me talk about exponential functions. So exponential functions is these basic ones. So you have 2 to the x and 2 to the negative x. So know this basic format. This is all exponential. We didn't get into a lot of it yet. I'll do a little later. Exponential growth and decay. We'll talk about that. Then we graphed a bunch of these. So just practice some of those graphs. We talked a little about this function, 1 plus 1 over x to the x. This function, as you approach infinity, converges, we say, to a finite number. So it converges to e, the number e. So e is approximately that, 2.71828, and then it doesn't repeat after that. It's irrational, and it's greater than 1, so it has this basic form, basic shape. So it's the increasing function. So your calculators all have e on it, not like 2 or something. It's e in base 10 is what we use mostly. We went over compound interest formula, did all that, and derived it. So just this would be a, evaluate type of example. Later, we're going to solve for that variable up here using the techniques we'll look at later. I think it's the next section. But this is, basically, finding those results. So that's a good example to do. Went over the derivation. I wouldn't ask you the derivation. I want you to see how we do the content, how mathematically we derive stuff. So we did all of that. Okay, and then we got into logarithms. So basically, we talked about this rational, this example, this concept. If the concept is, if you have a function that's 1-to-1, there must exist an inverse. We show that the exponential, both cases, are 1-to-1, right? Horizontal line test. If a function is 1-to-1, there must exist an inverse. Okay, and we actually know what it looks like. It's reflected about the line y equals x, like this. Okay, so you reflected about this line. And if so we know the graphs of each, and they exist. And we also know the domain and range, right? So the domain of an exponential is all reals, and the range is positive reals. So the domain and range of its inverse must be switched. And you can see that with the graph itself. So we talked about that. Let's see, where is it here? So this is the domain and range stuff we talked about. Okay, and then we looked at the composition. So what we say then is an inverse must exist for b to the x, and we call it a logarithm. So we say log base b of x. All right, so they're inverses, and they hold all of the inverse relationships. This is a really important formula to understand how these work. If you understand this formula, you will really kind of get this whole section, next couple sections. So try to work with that more. All right, then we looked at the definition, and I changed the variable to kind of illustrate how this works better. I don't like using x and y here. So if you know z is b to the w, then you say the exponent must equal the logarithm. So this is just playing with it, converting back and forth, simplifying it. Then evaluating it, and the way I like to evaluate it is set it equal to the exponent if it's a logarithm. And then you put it in that form to solve. So these are basically what I call nice examples that work out nice. Then we got into the basic properties of logarithms. And all this is derived from the above, all the above examples, basically. So know the inverse properties, inverse relationship. I think I wrote that there. Okay, so then we talked about some special cases. Common log is base 10. That's the common log. And then base E is the natural log. Right, and then that's what your calculators have. Calculators have base 10 and base E. Okay, so go over all that stuff. And I will be posting all this stuff, the video and my lecture notes online on Canvas. Okay, we did some graphing. This was like the next day. We did a bunch of graphing of logarithms, so go over all that. So then we left off in 4.4, I believe, properties of logarithms. Just got to know, understand product property, quotient property, power property. Know how to apply those. I did some proofs of those, the product and power. And then we applied the properties. So be able to expand out and like that, expand again all the way out. And then collect. So it looks like we need to do some collecting. Okay, so we'll do some of that. I think I went on to change, that's what I remember now. I went on to change a base just so you can get started on it. What I need to finish now is going the other direction. So we need to go back. Okay, so let's do some of that. See if I have an example here. Okay, so this is combine to one logarithm. Okay, so let me just start here. So we did the change of base formula like that and did a couple examples here and here. So let's do one more example of change of base. Let's just start there. All right, so more examples. Let's get rid of that. All right. So I have another example ready to go here for that. Change of base. Let's try this one. So what if you had log base 5 of 3? All right, so we want to be able to evaluate that. So our base 5 isn't on our calculator. We want to get an approximation for that. So you want to change it to whatever base you want. So as above, you can change it to base 10. So you just say log base whatever's inside 3 over log base 10 of 5. So that's a 10 there if you don't see it. Or you can do natural log. I use natural log because it's easier to write. Log base E over of 3 over log base E of 5. And then you get your calculator out and do that approximation. So I will do that. Let's get my calculator out right here. Do 3, and then I'm going to do ln, if I can find it. There it is. I get approximately 1.0986123, and it goes on and on. I'll actually going to keep my decimals in there. And then 5, and then do natural log. I get 1.609438, and then I'll divide those, and I get 0.68260, and we'll just say 6. That's enough decimals. All right, so you'll be able to use your calculators to evaluate that, and it's an approximation here because this is an exact form, and then you get your approximation. All right, so let's go the other way now. So now we want to combine to one logarithm. So that's I went on to this so you could use change of base, but we hadn't done combine to one log yet. So let's just go to this next page here. Okay, so the example, combine to one log. So suppose you had 5 log base 10 of C minus 4 log, and then that's again base 10K. And you want to, so that was the question. So you want to bring up the powers first. That's the first thing we need to do. So it's log C raised to the 5th minus log K raised to the 4th. So you can't apply the quotient property until you had, because the quotient property has no coefficients in front. So right here has to look just like that, 1 and a negative 1. Now you can apply the quotient property. So you get log C to the 5th over K to the 4th, like that. Okay, and it's base 10. All right. All right, so try more examples like that. I'll write this up, but I'm not going to use as much video space for this. So I'm going to write the example down, and then you can work on it. So it's 1/3 natural log of t plus natural log of t squared minus 9 minus natural log of t minus 3. All right, so I'm going to go ahead and stop there. And then that's it for 4.4. So work that out. I will have this posted on